So theta is equal to delta times, so u bar we've just found out to be this, so this is essentially 2y bar minus y bar square, thus allowing us to write 2y bar minus y bar square times 1 minus 2y bar plus y bar square dy. So this has to be integrated from 0 to 1, because it doesn't make sense to do an integration from 0 to infinity, because beyond the boundary layer the velocity profile as such becomes 0. Okay, as we go beyond delta, this contribution becomes 0, hence we do the integration from 0 to 1. It is very easy, but still let's do the labor. It's quite boring. So what do we have? Minus y raised to 4 plus 4y bar cube minus 5y bar square plus 2y bar dy bar, and this is equal to minus 1 by 5 plus 1 minus 5 by 3 plus 1. This is not dy bar. So this is equal to 2 minus 28 by 15, this is times delta, so this is equal to 2 by 15 delta. So this is what you obtain as the momentum thickness, 2 by 15 times delta. So we've just obtained that the momentum thickness is 2 by 15 delta, and thus tau wall by rho is equal to ddx of u infinity square times 2 by 15 delta. So the velocity profile, if we recall, is simply 2y by delta minus y by delta whole square. So in fact, from this particular equation also we can find out what tau wall is. So mu del u del y is nothing but mu du dy, which is nothing but u infinity times 2 by delta. Simply take a derivative of this. So u infinity goes over here and this y goes, and then we have taken it at y equal to 0, so the contribution from this term goes, because essentially del u by del y is equal to u infinity 2 by delta minus 2y by delta square. And then when you set y equal to 0, this term goes, and hence you get tau wall equal to this. So let's write down this particular equation when we have substituted the wall shear stress from this particular equation. So mu u infinity 2 by delta is equal to u infinity square ddx of 2 by 15 times delta. There is nothing but 2 u infinity square by 15 d delta dx. So mu so there is tau wall by rho. So this is tau wall by rho. So mu by rho, this u infinity cancels. So you take u infinity over here, and then this 2 and 2 cancels. So this 2 cancels. So you have simply 1 by delta is equal to 1 by 15 d delta dx, which implies delta d delta dx equal to 15 mu by rho u infinity. Delta square by 2 is equal to 15 mu x by rho u infinity plus constant, and then we use the asymptotic condition that as x tends to 0, delta equal to 0, because near the origin of the plate, while the boundary layer theory is not strictly valid, we can take an asymptotic limit, and thus c becomes 0, and thus delta square is equal to 30 mu x by rho u infinity, essentially implying that delta square is equal to 30 mu. So if I divide by x square, I have rho u infinity x. This is 30 by rex, and thus we obtain delta by x is equal to square root of 30 by square root of rex. So this is in line with the initial scaling that we had done, that delta by L. So we had obtained initially that delta by L scales as 1 by square root of re based on the length scale L, and this is what we obtain using an integral approach. We obtain delta scales as x times square root of 30 by square root of re based on the length scale x. Okay. So this scaling that we had, we did not know what the constant is, but now we are actually getting that constant to be square root of 30. Now obviously, if you have a better correction on the velocity profile, you get a better approximation of this. So how do you obtain a better velocity profile? If the flow outside is uniform, we can have another boundary condition that we can make the velocity profile satisfy. So let us write down the x momentum equation. So if there is if the flow is uniform outside, then this term becomes 0. There is no extra pressure gradient, because we know that del p del x is equal to rho u infinity del x. And so if u infinity does not change in x, then del p del x is 0, and hence this term is 0. So we have u del x plus v del u del y is equal to nu, so which is mu by rho del 2u del y2. And thus if we take the equation at y equal to 0, this term becomes 0 by no slip, and this term becomes 0 by no penetration, and thus you have del 2u del y2 is equal to 0. So you have this extra boundary condition that you can satisfy. So then essentially you need to satisfy these 4 boundary conditions. Y equal to delta, u equal to u infinity, y equal to delta, del u del y equal to 0. So these 4 boundary conditions, when you use, you can form a cubic polynomial, which I allow you to do it at your free time. So earlier we had just done the quadratic version, but this should allow you to obtain a cubic polynomial, and then you have to do the same thing again, and then you will see you get a better approximation to this particular constant, which checks out with the Blasius solution, which is not a part of this course. Alright, so please go through this derivation. It's really simple, and you have to make an approximation of the velocity profile. That's what the crux of the problem is. Good luck.